All right, so in chapter 4, we're going to be looking at polynomial functions. And today we're going to graph and analyze those functions. So the first thing we're going to talk about is the end behavior and the power function. So a power function is any function where you have this form. F of x equals ax to the power of n. And a and n have to be non-zero because if they were zero, then everything would go away. Multiplied by zero. Okay, or if you raise something to the zero power, do you guys remember what happens? Anything to the zero power is 1, right? So x to the 0 would be 1, and then you wouldn't have that function anymore. Okay, so for this power function, we call a the leading coefficient. So this is, I just abbreviated it, the LCO. That's the value in front of the term with the highest exponent. So in a polynomial, you can have multiple variables. The one with the highest exponent, that value in front is the leading coefficient. And then we call the value of n, which is an exponent, the degree. Okay, the degree is just the highest exponent. Okay, and in Algebra 1, you classified polynomials by their degree, and then also how many terms they had in the function. So you're going to see that come back around in this chapter. All right, so let's look at the next set. So the end behavior of a monomial function. So whenever you are doing the end behavior, you are just describing in what direction the ends are going. Okay, so we're going to look at some similarities here. Okay, you have an even degree, okay, and an even degree, and then an odd degree and an odd degree. Okay, so one thing I want you to do is I want you to look at those graphs, okay, and then see if there's anything you notice based on the degree. There's something you can tell about the graph based on whether the degree is even or odd. All right, and then James, is there something you picked up on?
Oh, I had a question.
Oh, yeah. Yeah. Oh, I didn't bother. Okay, so if the degree is even, what do you guys notice about the ends of the graph? Yep, that's exactly right. They go the same way. Okay, so we're going to write that down underneath here. So if the degree is even, okay, that means the ends go in the same direction. Okay, and then based on that, I want you guys to either write down or just think about it if you're unsure. What happens now when the degree is odd? Okay, so if you recognize it from the graph and you're ready to write it down, you can do that. If you want to have an answer in your head and wait to confirm, that's okay too. You can just think about it for a moment. Okay, and then Natalie, will you share with us what you wrote down about if it's odd? Yep, that's exactly right. So if the degree is odd, the ends are going to go in opposite directions. All right, now there's a couple other things we got to look at here with the end behavior. So we're looking at what patterns we can pick up on. So in the first two graphs, it says the leading coefficient is positive. In the second two graphs, it says the leading coefficient is negative. Okay, so I want you to examine those graphs. All right, and then I want you to talk with your row, and I want you to come up with a rule for what happens to the graph when the leading coefficient is positive, and what happens to the graph when the leading coefficient is negative. Okay, and it's okay again if you don't want to write it down, if you just want to talk about it. Okay, if you're unsure, you can tell that to your group as well. Okay, so I want you to touch base with the people in your row now. All right, Riley's going to tell us what her group came up with for if the leading coefficient is positive, what happens? Yeah, so they noticed this part. If it was positive, as x goes towards infinity, f of x goes towards infinity for both of them. And then, Evie, can you expand on that? Evie, can you expand on that? What does that mean? As x goes to infinity, what does that mean? Yep, on what side? I heard you talking. Yep, on the right side. Okay, so remember, as x goes to infinity, that means what's happening on the right. Okay, it's always about the right side. So if it's positive, it goes up on the right, or we can say it rises on the right. Okay, and what we're going to do is we're just going to highlight that part in our graph. Okay, so it goes up on the right side. Sometimes people want to say, oh, it goes up on the right, and then they want to say it goes down on the left. But let's examine our graph. So if it's negative, does it go down on the left? No, what's the thing? Yep, it goes down on the right. Okay, so the second one is all about the right side. Okay, so this, you can say it falls, you can say it goes downward. Okay, but make sure with both of those, you have it is on the right side. Okay, so when we do this, we're going to talk about our end behavior statement. So you have your end behavior statements here on your paper. The end behavior, the end behavior, the end behavior, the end behavior. Okay, so we're going to just do some annotations here. This says as x goes to negative infinity. That means on the left side, the graph is going to be going, and if it's positive infinity, it's up. Okay, if it's as x goes to positive infinity, that is right. Okay, and then this again would be up. So remember that you have two ways to talk about infinity and negative infinity. Okay, we're going to do this one together, and then we're going to write down a statement where you are going to be filling in the blanks as you do this practice. So this is still as x goes to the left, f of x goes down. So on the left side of the graph, it's going down. And then this is telling you on the right side of the graph, it's going up. Okay, so one thing that we can decipher from these statements is you're always going to have a left side of the graph and the right side. Okay, you always have two ends. So when we're creating our statement, okay, we're going to call this the EB statement. And I notice some of you might not have room here. That's okay. You can squeeze it in where you have room. Okay, so as x goes to negative infinity, f of x goes, and then that changes based on your graph. Okay, but they're always going to have a right side and a left side. Okay, so as x goes to the left, what does the end do? As x goes to the right, what does that end do? That is what we're going to be writing down today. Okay, so that statement there, that's what you're going to be filling in whenever it says to find the end behavior. So our symbols are going to represent two things. We're just going to write those down as well. So anytime you're working with the x values, if you want to signify you're going to the left, you use negative infinity. If you want to signify you're going to the right, you can just use infinity. Okay, in some textbooks, you also might see positive infinity, so like a little plus in front, and that's okay too. All right, now for the y's, just like the y-axis is vertical, it goes up and down. The x-axis is horizontal, it goes left to right. The y is going to have a symbol for going down, which would be negative infinity, or up, which would be positive infinity. So depending on if you're using x or y, negative infinity can either mean left or it can mean down. Positive infinity means up or it means on the right. Okay, we are going to tackle the first part of this where it says describe the end behavior. Okay, and it says you have to use the leading coefficient and the degree, which just means you aren't going to graph it. You aren't going to look at the graph. And then it says and state the domain and range. We are going to do that in a second. Okay, what I want you to do is I want you to write down the start of this statement. As x goes to negative infinity, where does f of x go? As x goes to infinity, where does f of x go? Okay, so we're going to use the leading coefficient and the degree. So if we look at the leading coefficient here, okay, we can see the leading coefficient is 5. We just have to determine if that's positive or negative. Okay, so the leading coefficient is 5. That is positive. Okay, remember we just said if it's positive, that means it's going to go up on the right or rises on the right. Okay, so which one of these is the right side? Is x goes to negative infinity or is x goes to positive infinity? Positive infinity. So we are going to fill in the bottom one first. Okay, so if it's positive, it rises on the right. This will be positive infinity. And the next thing we're going to do is look at the degree. So earlier today we wrote down the degree is the highest exponent. So I want you to write down what the degree is. And then see if you can fill in that other blank based on our rule. Okay, and once you finish that, if you would like to do the same thing for part B, you can get started there. And then I'll come around if you need some help and just check that you got your First one filled in. Okay, so Izzy, what did you determine from the degree here? It is going to be positive, but for the degree, just remember it has to be either even or odd. So your leading coefficient is positive, and then if it's even, what does that mean about the ends? Yep, they're going to go in the same direction. Good. Okay, so if they're going in the same direction, if you got infinity here, positive infinity, this is also going to be positive infinity. Okay? All right, and then it looks like you guys did a nice job setting up the second one. Okay, and then Abian, can you tell me about the leading coefficient for this one?
Negative.
Yep, and so if the leading coefficient is negative, what does that tell you?
It's falling on the right.
Yep. So if it's falling on the right, that means the first thing we're going to put in is this negative infinity, okay? Then you can look at the degree. Okay, and then Charlotte, what's the degree for part B? 5. Okay, so then you determine if it's even or odd. 5 is an odd number. Okay, and then remember what we wrote down up here. If it's odd, the ends go in opposite directions. That's actually how I remember it. ODD, OPP, odd, opposite, they fit together. And then if you go down here, this is going to be up. Okay, so you can always fill in that one first. All right, now some of you did a really nice job noticing what is happening with your domain. For all of these, what was your domain? Cal, did you write down your domain for all of them? Yeah, what'd you get for that? All real numbers. Okay, so your domain is all real numbers. So when we're writing our domain, we are going to be writing these in interval notation. Okay, so if it's all real numbers, it's negative infinity to positive infinity. Okay, and so for the domain, we are going to write negative infinity to positive infinity. And that will be the same for both of these. So I'm going to sneak this in here. All right, and then let's look at our range. So for the range, that is going to change. Sorry, that rhymed. Okay, so sometimes it's going to be all real numbers. Okay, so it's all real numbers when you have what kind of degree? Odd. And that's because it goes from negative infinity to positive infinity. Okay, so anytime you have an odd degree, the range is all real numbers. So for this, the degree is even. It's not going to be all real numbers. This one, the degree is odd. It is going to be all real numbers. Okay, so all real numbers, odd degree. Okay, the range, if it is all real numbers greater than or equal to 0, when we write that as an interval notation, okay, we're going to write that as 0 to infinity. Okay, if they are below the line, that's when you have the negative coefficient. That would be negative infinity up to 0. Okay, because if the graph is falling, it will be below there. Okay, so all of these are above. Okay, if it's a positive coefficient, it's below if it's a negative coefficient. So if it's positive, it rises. Okay, if it rises, that means it goes to infinity. So 0 is where it starts, and then infinity is where it will go to. Okay, so those are the rules you're going to be using for your end behavior. All right, and then for example 2, if you guys have your graphing calculators, you can use that for this part. So a scientist models changes in ocean density layers by using the function f of x, where x represents the distance from the equator. Okay, when it says to graph the function, I'm just going to let you draw a sketch of that from your graphing calculator. Okay, so when I say draw a rough sketch from your graphing calc, you don't have to put it on graph paper. And then you are going to have to adjust your window to see your full graph. Okay, so let's plug that in. All right, so we have 0.0006 x to the 4th minus 0.7 x squared minus 100. All right, so I cannot see my graph, so I'm going to go to zoom. You can either zoom out, okay, and you can see part of your graph. Okay, and then we're going to zoom out again. And then sometimes your zoom fit also works. Okay, here I can see more of the graph. I'm going to go to my window now. So my x's are fine, but my y's I need to go further. So I'm going to try negative 250 to 250. And then your scale, you can go by tens on each of these, and then you'll be able to see the tick marks there. Oh good, that's better. So maybe I want to go to negative 400. Okay, just so I can see that full shape. Okay, so you do need to adjust your window. To see the full graph. Okay, and then that can be your rough sketch. Okay, and then it says to state the domain and range. And then it should, oh yeah, it says round to the nearest 100 if necessary, because you have some large numbers here. Okay, so your domain, if you look at these, this is slowly going to negative infinity and infinity. So just like before, your domain is going to be all real numbers. So negative infinity to positive infinity. Okay, and then when you are calculating your range, remember, your range is going from your lowest y value to your highest y value. That's why we need to be able to see this. Okay, now the highest y value is what? According to our graph. Infinity. So that is going to be the second part is infinity. Okay, the other part is going to be a number. We have to find the minimum value here. Okay, so we can use the minimum. There might be other cases where you have to use the maximum. Do we remember how to get there? Second calc. Then we're going to go to the minimum. Okay, so I want you to see if you can find that from last time. And if you don't have like the bottom of the graph showing, remember you just go to your window, make your y value lower. Okay, so the left bound, I'm going to go to the left side, the right side, and then you can do a guess. Okay, remember it says to round to the nearest 100. So I got negative 304.1667, of course. And let's just double check this one here. Okay, this one is symmetric, so it should be the same, but okay, and then again, we have that negative 304.1667. Okay, so if we're going to round that to the nearest 100, okay, it would either be 300 or 400. Obviously, this is closer to negative 300. Okay, so this is going to be your domain and range. Okay, and then if you don't have your graphing calculator, if you're in a pinch, there is a TI-84 app if you're at home and you don't have your graphing calculator, okay? All right, the next thing we're going to talk about are polynomials. So a polynomial in one variable is an expression of the form a sub n x to the nth plus a whole bunch of things. Okay, so I just want to show you how they're coming up with this because this is something that you'll see often. So it's a sub n x to the nth power. Okay, the a sub n stands for, it's the leading coefficient to the variable with the exponent of n. Okay, let's say n was 5. What would n minus 1 be? 4. And then the next one would be n minus 2. It would be 3. All the way until you get to x to the second, then x to the first, and then no x. So they're just giving you a generic polynomial here. And this is going to be where n is a non-negative integer. So that means that you can't have a negative exponent. So if they tell you n is a non-negative integer, what that means is there are no negative exponents. Okay. X to the power of negative n is equivalent to 1 over x to the n power. Okay, that would not be a polynomial. Now, it says integer. I guess I should have done that from your non-negative. Your integer means you can't have any fractional powers. So that part's the non-negative, this is the integer, and you can't have any square roots. So that would be something like x to the 1/2. X to the 1/2 actually is the same thing as the square root of x. We'll talk about more about that later on. Okay, and then it says because the terms are written in order from greatest to least degree, this polynomial is written in standard form. Okay, so anytime you have a polynomial in standard form, the exponents go in order from greatest to least. Okay, so you start with the largest exponent and then you go to the smallest. Okay, so exponents go in order from greatest to least. Okay, and then the degree of the polynomial is n, and the leading coefficient of that would be a to the nth power. Sorry, a sub n. Okay, so your degree is the highest exponent. Okay, and then it says a polynomial function is a continuous function that can be described by a polynomial equation of one variable. You have learned about the constant, linear, quadratic, and cubic functions. A quartic function is degree 4. A quintic function is a 5th degree. Okay, so quartic, I remember that because there's 4 quarts in a gallon. So quarter, quartic, 4. And then quintic, I grew up with this toy and it was called Quintuplet Surprise. And there were 5 babies that came in there, and the surprise is if it was a boy or a girl. So I remember if you have 5 kids at one time, they're called quints. So a 5-degree polynomial is quintic. Okay, and then this last thing is something we're going to write down. It says the degree tells you the maximum number of times that the graph intersects the x-axis. So that's going to be related to your x-intercepts. So whatever your degree is, that's the max number, the most amount, max number of times the graph crosses the x-axis. Okay, so if the degree is 5, it couldn't cross more than 5 times. Okay, it could cross less, but not more. Okay, so for our next example, you're going to state the degree and the leading coefficient. Okay, and if it's not a polynomial, you have to explain why. Okay, so I'm going to give you the equations. Well, these are going to be expressions. There's no equal sign. Okay, so we have 8y plus 7y squared minus 9y cubed minus 15y to the 4th. Okay, so you either state the degree and the leading coefficient, or if it is not a polynomial in one variable, just tell me why. Okay, these are not necessarily in standard form. Okay, so it does say that these are the polynomials in one variable. So here we have the variable y. This is not in standard form, but it is going to be a polynomial. If it's not a polynomial, you'll usually see a negative exponent or a fractional power. We don't have this here, so the degree is the highest exponent. The highest exponent is 4. Okay, and then the leading coefficient, do not forget the negative in front. Okay, so the leading coefficient is negative 15. Okay, 4 is the highest exponent, so that is going to be the degree. Okay, in Algebra 1, you probably had to write these in standard form, and then you set the degree and the leading coefficient. Okay, now this one, you have x in all of them, but here, you see your x squared is in the denominator? When that happens, this is the same thing as saying 13x to the negative 2. Okay, so I'm okay if you say this one of two ways. You can say it's not a polynomial because you can't have a negative exponent. Okay, or you can say it's not a polynomial because you can't have a variable in the denominator. Okay, either one of those are fine. So a variable in the denominator is a negative exponent, so it's okay if you use that terminology. Okay, but you do have to state that it's a variable in the denominator that's a problem. It's not going to be a problem if it's a number. Okay, it's only if it's a variable. Okay, now because this says one variable, this one is not going to be a polynomial in one variable because how many variables do you have there? You have 2. Okay, so this one is not a polynomial in one variable. Because you have two variables, A and B. Okay, so if it specifies it has to be in one variable, then you can go ahead and list that as your reason. Okay, you're really going to like the next one because it's very simple. You can remember the rule. So it says use the graph to state the number of real zeros of the function. Okay, the number of real zeros is equal to the x-intercepts. So the x-intercept equals the real zeros. And all we have to do then is count what our x-intercepts are. So 1, 2, 3 x-intercept. Your answer for this is going to be 3. Okay, so go ahead and do part B. That's in your answer. All right, and then Lawrence, what'd you get for part B? 2. Good. Okay, now for these mixed exercises, this is going to combine a few things that we talked about today. So it says describe the end behavior. Okay, that's one thing we have to do. We have to state the degree and the leading coefficient. Okay, and then if the function is not a polynomial, explain why. Okay, so if it's not a polynomial, again, you're going to see either an exponent with a variable in the denominator of a fraction. You're going to have two variables, or you're going to have a fractional power. So if you don't have those, it is a polynomial. Okay, and it does say to describe the end behavior first. I would identify the degree first and the leading coefficient. Okay, and then when you're doing your end behavior, you can always, sorry, they just say this is g of x, so we'll call it g of x. You can always start it out the same way, okay? All right, I'm going to give you a minute to try that. All right, the rule for this one, Alyssa, what did you get for the degree? Yep. Okay, so if it's a 5, and it does say to state the degree, so it's 5. I also want you to just make a notation that it's odd. So what does odd mean? They're going to be going in, yes, opposite directions. Great. Okay, and then if the degree is 5, the leading coefficient would be in front of x to the 5th. Now here, this doesn't matter if it's odd or even. It matters if it's what? Yep. So this is positive, so it goes up on the right. So when you go to fill this in, up on the right means this is going to be infinity. If it's opposite, this is going to be negative infinity. Okay, and it is a polynomial, so we don't have to worry about doing that step. Okay, the reason why I wanted to wait to do part B with you is because it's a different form, and I don't want you to jump to conclusions. So this is x plus 5. And remember, this means times 3x minus 4. If you are given a problem in this form, what we're going to have to do is FOIL. Okay, so we're going to multiply. We're going to FOIL that out. So I'm going to give you a moment to try that by yourself. That way you're thinking about the process and not just copying me down. Okay, and then once you do that, then you can do the degree and the leading coefficient. Okay, so when you multiply 3x times x, you get 3x squared. I like to do the middle, the inside. So 15x, then the outside, negative 4x minus 20. Okay, so my polynomial is 3x squared plus 11x minus 20. Okay, so based on that, we can find the degree. So degree is the highest exponent, so it's at 2. The leading coefficient would be the 3, and then that's going to tell you a few things. Whenever you are setting this up, okay, I'm showing it to you like this so that you can always fill in this last part, because you always need to know what happens on the right side and the left side, and then that can give you some time to process. Okay, some of you are going to catch on to that a little bit quicker, and that is fine. So with the degree, it's even. With this, it's positive. Anytime the leading coefficient is positive, on the right side, it goes up. If it's even, they are going to the same place. Okay, so this is your end behavior. Okay. All right.